Now we're ready for Module 9. We're going to talk about rational functions. Rational numbers are fractions, and so we're going to take a look at what that is going to give us as far as functions. So a rational function is formed by the quotient of two polynomial functions. So we want to actually think as the numerator as being one function, the denominator is a second function. In the denominator, it needs to be a non-constant function. Constant, what I mean by constant is just a single number, because that's not really a rational function, right? If we just had something like x squared plus 2 over 9, that's not what we're talking about as a rational function. But if it was over 9x, all of a sudden this is a rational function. So again, we think of a rational function as being a numerator of a polynomial, having a polynomial value, and the denominator being a polynomial. Again, the denominator is not constant, and additionally, the denominator cannot be equal to 0, because that gives us this problem we've been having as we talked about domain of division by 0. And actually, we're going to see that this issue of where q of x would be equal to 0, that is going to give us a special feature of the graph. And so rational functions, we basically have two important features to take a look at. And so that's what the discussion will be today. The first one is when that denominator does become 0, we get a vertical asymptote. And that's when the x value gets close to some value of a, so whatever, we'll look at some. In this top one up here, if x became equal to 0, that's going to give us a vertical asymptote, right? Because 0 times 9 is 0, so we get division by 0. And so what's happening is the function itself is going to be either increasing or decreasing without the bound. So it's either going to be going up to positive infinity, and generally on one side it'll go to positive infinity, and then on the other side of 0 it'll go to negative infinity. Generally what we're going to see. Not always, but again, most of the time that's what we're going to see. The other thing that can happen, or that does happen, is that these ratio of since we've got two functions, one in the top and the bottom, the way the ratios interact with each other can cause something called a horizontal asymptote. And that's when the output value gets very close to a number. So again, in these cases, this is going to be in behavior type stuff. In behavior stuff. So as x is getting either towards positive infinity, that's what it means to increase without bound, or decreases, which means it's getting close, it's going towards negative infinity. So as x is going either to the left or to the right, way out to the extremes, we'll see functions that approach a particular horizontal value. And so that gives us a horizontal asymptote. So let's look first for vertical asymptotes. Again, that's going to happen whenever the denominator becomes equal to 0. So in the past, we just looked at this as 3 minus x equals 0, and we were looking at that would be, it'll give us the number that we need to exclude from the domain. We can add x to both sides, and what we get is that 3 is equal to positive x. So that is, and what we want to see with this now, that is a vertical line. So if we were to graph x equals 3, here's 3, what that is it's a vertical line. And what we're going to see is this graph coming from one side or the other. Now, from the left side, so if x is less than 3, this number is going to be positive, right? 3 minus some number less than 3 is going to be a positive value. That's going to be positive. So what's going to happen, and x squared is going to get much bigger than this. What we will see is potentially something where the graph is going to be going towards positive infinity. As we get bigger than 3, so plug in like 4 minus 3, that's going to be a negative value. So the indication is it's probably going to go down to negative infinity. And what exactly it looks like, we're not quite sure. We're going to talk about horizontal asymptotes in a moment, but what we can see here clearly, when the denominator comes 0, we're going to get a vertical asymptote at x equals 3. So let's go ahead and do a graph, and we'll just verify everything with the graph. So just put y equals, what did we have? We had x squared divided by 3 minus x, 3 minus x. Oops. Some other things, there we go. We just want that. And so actually, because of the x squared, that's why I was wondering, okay, we're going to get a square out of it. We actually didn't get any problems. We get this 0, 0. So when x is 0, y goes to 0. But when x is 3, that's what we're looking at. We would expect, and so we'll put that in there, x equals 3. And that's what I like about Desmos, is we can actually graph these asymptotes. Most of your other graphing calculators won't let you do that. Okay. We'll go out a little. Oh, there it is. So there is a part on the bottom. See, sometimes you just have to, I was going, what? Maybe I was way off. But I'm not so bad. It's, yeah, there's this part down in the bottom. So this one is, as it gets close to 3, the y values are going towards negative infinity. And as I come from the left and get close to 3, the y values are going to positive infinity this way. So I wasn't too far off. Just know, yeah, there's an x-intercept there. So we'll look at those kind of things. But sometimes that's why I always feel it's important to kind of look at the graph, because sometimes there's unexpected things that are happening. So we can take a look at that. Clear off this stuff. Always the best way to do things. So we come back here, and we've got one more that we'd like to take a look at. And I'm kind of setting up, we're going to look at this one in really in detail as well. But I want to look at something when we talk about vertical asymptotes. And so let's do this. So yes, we do need to concentrate on the denominator. When does the denominator become equal to 0? So x squared minus 9 equals 0. Hopefully you recognize this as a difference of squares. You could just add 9 to both sides and take the square root, and then you get plus or minus 3. But what I like to do is go ahead and factor x squared minus 9. That's a difference of squares, so we're going to get x minus 3 times x plus 3 equals 0. And so then we might look at that and say, okay, we're going to get asymptotes at positive 3 and negative 3, because this will solve out x minus 3 equals 0. So x equals 3. And then we'd say x plus 3 equals 0. Subtract 3 from both sides, x equals negative 3. So we're thinking we're going to get asymptotes at both these places. Now, you might think, well, he doesn't sound so confident. You're right. So I'm going to come back here. Let's go ahead and graph this. So we've got y equals, what did we have? We had x minus 3. Good. X minus 3. Back that up. So we select the whole thing and then we divide, and that's going to give us, so now we do x squared minus 9. And we do see the asymptote here at negative 3. So, well, we might not, but we see the spacing there. So I'm going to put that in. Oops, not my x equals, right, we're getting a vertical line, x equals negative 3. We see that that seems to fit well. But if we put in the asymptote of x equals positive 3, that's not working there, is it? So there really isn't an asymptote there. There's not, but there is something. There's something missing. Watch as we come along here as we get to 3. At 3, it's actually undefined. There's a hole in the graph here at 3, and that's what I'm going to explain. So I wanted you to see it because a lot of times seeing is believing. So instead of an asymptote, we just get a hole in the graph. And why did that happen? Well, some of you might have noticed as we were going along that we have a numerator here of x minus 3. So wouldn't this x minus 3 over x minus 3, x plus 3, wouldn't we get this to cancel out? And you're right. And then we get 1 over x plus 3. If you graph this, you'll see it really is the same thing as what we have here, except it won't have a hole there. So this one has a hole at 3. The other one, with getting rid of that factor of x minus 3 completely, the only difference is there is no hole. And again, you don't have to believe me. Sometimes, like I said, seeing is believing. So we'll do a y equals 1 divided by x plus 3. And we see, yes, it looks like it's exactly the same, except now that we're on the purple graph, we come here and 3 actually has a value. Okay, so sometimes we can do that. So there is a difference between the red function and the purple function. And we'll talk a little bit more about it. But that's the other thing is you can't just look at where does the denominator become 0 and assume there's going to be an asymptote there, because we have to look at the full function. Okay, so we're going to come back to this one and look a little more detail after we talk about horizontal asymptotes. So horizontal asymptotes. When we look at these, we're looking what is happening as x gets really big. X is going towards either positive infinity or x is getting really small. In this case, I like to think of it as big in a negative sense, but I know that's a small number, but I don't know, debt is oftentimes considered a negative number, and if I had $50 million in debt, I wouldn't consider that a small thing. So anyway, this is what we're considering when x is really, really big. So when x is really, really big, we get to ignore pretty much everything about the polynomials except for the largest degree, both in the numerator and denominator. And that's what we're going to do, and that's sort of how we examine things. Okay, so let's see. We're actually going to end up with 3 different cases, 3 different things that could happen. And so the first one, let's look at what happens when the degree of the denominator is larger than the degree of the numerator. Okay, so let's just kind of make up an example here. If I have 3x to the 5th plus 4x squared minus 2, what's going to happen to that versus 5x to the 7th plus 2. That's all we really need. Again, as x gets large, in the numerator, everything else is much smaller than something to the 5th power. Take a big number to the 5th power. This other stuff could add to it, could subtract, but really we can ignore it, and we're going to. In the denominator, same thing. We just need to worry about the thing with the largest denominator. So yeah, as x gets 100 million to the 7th power, that's pretty big. You don't even have to consider add 2 to it, right? So we're able to analyze these by just taking the ratio of the top and the bottom. And we can do this for each case. But the thing is when the degree of the denominator is larger than the degree of the numerator, what's going to happen, okay, we still got this 3/5, right? Those are there. But we get some canceling, the 5 and the x to the 5th and x to the 7th, we end up with x squared. So in the long run, this is going to act like this. And as x gets very large, this is going to act like, really, thinking of infinity, 1 over infinity, which is going to get pretty close to 0. Okay, so when degree of denominator is bigger, greater. What's a better word? Bigger or greater? Greater than the degree of the numerator. The horizontal asymptote, I use an abbreviation here, is y equals 0. And let's take a look. Let's go ahead and we'll graph that out as I got it there. But what you'll see is from the analysis part, it's going to, in the long run, act just like 3 over 5 to the x squared. So and of course, I don't always, let's go here. Occasionally I'll do these and I make the exponents too big, and then the calculator can't even handle it anymore. So what did I do? 3x to the 5th plus 4, what did I do? X squared, I think I did. And then I did minus 2. And then I want to make this into a fraction, so I'll select that and divide. And then the bottom I did 5x to the 7th. What did I do? Plus 2, right? That doesn't make much of a difference. Now, as you saw, everything I did does make a difference of how it looks here. But as I get out to infinity, let me kind of, I get out towards infinity, we just see that line. Maybe I should, let's make it, okay, change the color on this one. I know what I can do. So when I use the pen, it doesn't work, but when I use this is how I can make it work. So notice it's the blue line. It's just getting close there to the x-axis, which is y equals 0. Okay. So that's what's happening there. So that's case number 1. Horizontal asymptotes y equals 0. The next case that we could take a look at case 2. So we've got the denominator is larger. How about what happens when the numerator is larger? So we could use kind of the same. What if we had, I don't know, 3x to the 7th over, let's just leave it 5x to the 5th. And we could have other stuff in here. We don't really care what else is in there, remember, because if these are the largest degrees, that's all we've got to worry about. What we're going to see is that this will reduce down to 5 from 7 is 2, so it's 3x squared over 5. Now this is a number that just, it gets bigger and bigger, right? Now that it's squared, it will be positive. So what we're going to see here is that as x goes out, the y's are just in both directions going to go up to infinity. There is no horizontal asymptote in a case like this, whenever the top is bigger. Now, in the notes, you may want to look at it when it's when the numerator is exactly 1 degree bigger than the denominator. You end up with a linear function, and you can get something called a slant asymptote. Take a look at that. We're not going to spend none of the questions that I've assigned that are assigned in this course have slant asymptotes, but it's worth taking a look at. You may see those in calculus. Okay, but so we do have an example in the notes, but we're not going to spend our time on it here. So just note that that's going to, basically act like an x squared, which goes off to infinity. And let's look at case 3, and then we'll look at them together. Okay, so case 3, what we haven't considered yet is what happens when they're the same degree. So notice, so this is numerator greater than denominator. Yeah, denominator greater than numerator, so that switches it. And then now, when the degrees are equal. Okay, and you'll see examples of all of these in the course notes in Canvas. So let's go with 5x to the third plus 2x, and in the denominator, let's go with 2x to the third minus 4. Okay. Again, all we have to look at is the two largest, and so we're going to analyze this as if it were just, and again, we ignore everything else because it doesn't matter as x gets really large. Well, we see that the variable parts will cancel each other out, and so indeed this will behave like 5/2. So it's the ratio of the coefficients in front. 5 divided by 2 is 2.5. So yes, it'll be the horizontal line at y equals 2.5 is where our horizontal asymptote will be. And so let's go into Desmos. We'll take a look at these two examples. And let's clear this one out. So let's just look at that last one that we just looked at, y equals 5x cubed divided by 2x cubed. And I guess I could put a little bit more into these just to show you that while having additional terms in here does affect what happens in the middle, we get something looking different. What it's doing in the long term, as we said, there's going to be a horizontal asymptote at y equals 2.5, and we see that going on right there. Okay, so everything is just fine. So let's come back to this function that we started with. We've already seen it has a hole in the graph, so we've examined that. How about now really, again, we did this earlier, right? Let's keep moving forward with this. It is x minus 3 over x minus 3, x plus 3. So we can analyze that. That simplifies down to being 1 over x plus 3. For the most part, we can analyze it with this simplified version, just realizing that we're going to have vertical asymptotes, certainly at x plus 3, or not at x equals negative 3, right? Because x plus 3 equals 0. Subtract 3 from both sides gives us x equals negative 3. And then we're going to have a hole, not actually an asymptote, but that we're going to have a hole at x equals positive 3. So that's that one that sort of canceled out. The next thing to consider is where is the horizontal, or is there a horizontal asymptote? And that's going to be by looking at the numerator over the denominator. We can look at this reduced fraction here. So it's going to behave like 1 over x. The denominator is larger than the numerator, so this is going to have a horizontal asymptote, y equals 0. That's going to be the x-axis. Okay, so let's do those in red and sort of make them dashed lines. So we're going to get a horizontal asymptote here on the x-axis. We are going to get a vertical asymptote at x equals negative 3. We can figure out all those things that are going to be happening on. It'd be nice if we could get a y-intercept, and so y-intercepts are where x equals 0. We put in x equals 0, we get that y equals, right, 1 over 0 plus 3, which is 1/3. So the point 0, 1/3, here's 1, there's a half, should be maybe about there. Let's do it in blue. There should be a y-intercept about there. Actually, we've already looked at this graph, so if you remember that, we're probably just fine. And then again, if you kind of analyze this all the way until negative 3, so negative 2, this is going to be positive. So as we get to close to negative 3 from this side, we should see this side going up towards positive infinity, and then we see this asymptote here, so it's going to kind of keep on going down. We do know at 3, we'll do that. At 3, we'll get a hole in the graph, so we'll put that hole there. We could, and actually, when we graph it with sort of its simplified form, we can figure out where exactly the y value of that hole is, and go from there. But we don't really need to do that. So then we can see on the other side. So as we approach negative 3 from going sort of this way, what we would expect to happen is, because of the asymptote, to come down like this and probably somehow go down like that. Now again, we could plug in a value of -4 and get a y value if we wanted to get real accurate. But with these sketches, these are all going to be just fine, because in the end, what we're going to do is we're going to go to Desmos anyway. But I wanted you to see one where we have a hole that cancels out. Sometimes that happens. Had we had like x minus 4 in the top, it would not have canceled out, and we get an asymptote. So a lot of times, just a small change in a particular value can make a big difference in how the graph ends up looking. So let's go ahead. We'll come back here. Actually, I don't think we need to graph it again. I think we still have it graphed. Here we are. Oh, no, that was that other one. Oh, I must have deleted it or something. So we'll go ahead and do this. Y equals, and we had x minus 3 divided by x squared minus 9. And again, we see what's happening here. See, there it is, 0 and 1/3. 0.333 is 1/3. And then if we trace along here, we see at 3, we get a hole. At 3, when x is 3, it's undefined. And you could figure that out. And then we got this bottom part going on here. And again, we could put in that vertical asymptote at x equals -3. And there it is. And let's see. Let me get a dashed line. Oftentimes looks better. And you can put in a hole. I think it ends up being the x coordinate we know is 3. Let me show you how to do this. And I think it's comma 0.167, I think is what it was. There's that dot. But watch now found out that it's with this, I can hold it, and we can actually put an open dot there. So we can make this as accurate as we want, as beautiful as we want. Got everything. The one thing I didn't put here was the horizontal asymptote though. So let's go ahead and do that. That's going to be at y equals 0. And we see that going, and it might be nice that we have all our asymptotes the same color. So let's make it blue and dashed. So we see our asymptotes that way. We see the hole in the graph, and that's the idea by using Desmos, is you're going to be able to draw everything very accurately. The idea of the sketches is to help you understand the principles that are going on. And so if you find it helpful to graph it first, and then as you draw the graph, kind of talk yourself through it. Why is each part of the graph being what it is? I think that'll help you as you move through this course into calculus as well. Okay, so this is the end of Module 9's direct instruction. You'll want to complete the learning activities for the module, and as you run into anything that gives you some difficulties, remember we have our online tutoring, we have our instructor office hours, and also we have our discussion forums to help everyone work together. All right, thank you very much.